Replace the force system by a wrench and specify the magnitude of the force and couple moment of the wrench and the point where the wrench intersects the XZ plane. Okay, so we want to reduce this force system. There's no couples, but if there was a couple, we could reduce that as well to a wrench. Remember, for a general force system, so it's not a special case. It's not the forces aren't coincident. They're not coplanar. They're not parallel. Just the general case. The simplest form you can reduce it to is you can reduce it down to a wrench. To do this, what we're going to do is we're first going to reduce this to a resultant force and couple moment at point O. That's what we've done in example problems in the previous videos. So we know how to do this. And then once we have that couple moment and resultant force at point O, we'll create the wrench from there. What we do is, so here's a couple moment at point O, and then here's the resultant force. And the resultant force and couple moment in general are in any random direction in 3D. From there, we break the couple moment down into a component parallel to the force and perpendicular to the force. Then we move the resultant force off of point O a distance that allows us to get rid of the perpendicular couple moment. This is what we did with the coplanar force system and the parallel force system. The reason that worked is because the resultant couple moment was perpendicular to the resultant force already, just naturally. That's what allowed us to just replace the system by a resultant force. It was two different systems, so the coplanar system and the parallel force system, the analysis was different, but the result was the same in that the resultant couple moment was perpendicular to the resultant force. And so that's why we could just move the resultant force off of the point, and then we had simplified the system down to a single resultant force. Well, for the general case here, we move the resultant force off the point, we get rid of that perpendicular couple moment, but we're still left with the parallel couple moment. But again, with simplifying these force systems, we're reducing it down to couple moments at points, couples. So these are free vectors. We can just move that couple moment vector to the point that the force vector is at. And you get this, at a point, you get this force vector in line with this couple moment vector, and that's what's called the wrench. I'm not sure why they call it a wrench. I guess to me it's more like a screw, because a screw, you're applying a torque, a couple, and also there's a linear force in that same direction. But it's called a wrench, and that's it. That's what we're going to do here. Now note that we're going to use point O as our point that we're going to first get the couple moment and resultant force at that point. But we could do this about any point. We could move the origin out here. We could do it about some point off the origin. You would get the same result in all cases. The wrench is going to be located at the same point in space based on this force configuration. But just like the coordinates of where the wrench is located would be different depending on where our origin is, you see? But again, in 3D space, regardless of where the origin is, you would have that same wrench position for this force configuration on this block, on this 2 by 3 by 0.5 meter block with these force magnitudes and directions. But we're going to use the origin, have the origin at this point on the block, and we're going to make our couple moment and resultant force, we're going to do it about this point and then create the wrench from there. And then this part of the question here, the point where the wrench intersects the XZ plane, to get this answer, we'll just need to know where the wrench is located. So to create a wrench, you have to create the wrench, right? You have to create the wrench. So the question wants us to specify the magnitude of the force vector and direction, and the magnitude and direction of the couple moment vector, but they're in the same direction. But also where's the tails of these vectors located at in 3D space. So once we have that information, we can use the line of action. We know the line of action of the wrench. We know a starting point, the tail of it. We can find a line in 3D space and see where does that line intersect the XZ plane. And that's how we'll answer this part of the question. Okay, let's get started. All right, so in the previous videos, we did problems where we found we reduced a system, a general system, to a force and couple moment at a point. Let's do that again. So the resultant force vector at point O, we just do a vector sum on all the forces, regardless of where the point is. So, all right, we've got minus 400 I hat minus 200 J hat. Okay, then positive, we'll use this force triangle, 3/5 times 200 I hat. Okay, right, it's positive X, and then plus 4/5 times 200 K hat. Okay, so this is 40. So, okay. Minus 400 plus 120 I hat minus 200 J hat plus 160 K hat. So this is minus 280 Okay, so there's the force vector. This is in newtons. Now, the direction of the force vector is important because that's going to be the direction of the wrench, right? So let's go ahead and get a unit vector in this direction. Okay, so the magnitude of the force vector $379.5. Okay, so U hat, and we'll label this as that for parallel, is minus 0.738 I hat minus 0.527 J hat .422 K hat. Okay, now let's get we'll kind of box this off here. Now let's get the resultant couple moment. So this is the vector about point O. Okay, so this 400 Newton force here causes rotation about the y-axis and the z-axis, but not the x-axis. So the y-axis, if we put our right hand along the y-axis, thumb in the positive direction of y, this is causing rotation in negative rotation about y. So 400 times the moment arm is 0.5, so this is minus 200 j hat. Okay, and then about the z, using the right hand rule. So again, put your right hand along the z-axis with the thumb facing positive z. The curl of the fingers is in this direction. So this is causing rotation in positive k hat, 400 times 2. So plus 800 k hat. All right. Now this 200 Newton force, it is causing no rotation about the z, no rotation about the y, just a rotation about the x. 200 times 0.5, 100 Newton meters. So, and this is in the positive I hat direction. So plus 100 I hat. Okay, now this force is in the xz plane, which means it's only causing rotations about the y-axis. So the x component, that's 3/5 times 200, okay, with a moment arm of 0.5, so 1/2. This is causing rotation in about the j hat. Is this positive or negative? Right hand rule. This is positive. Okay, now the vertical component, so we've got 4/5 times 200, and then this moment arm is 3. And this is also j hat. Okay, this is negative. Okay, so right. Okay, so all right, 100 I hat plus minus 200, and then we've got plus 60, and then minus 480, and then plus 800 k hat. Okay. 100 I hat, and then minus 200 minus 480 is minus 680. Minus 680 plus 60 is minus 620. Okay, there we go. That's the couple moment. So we're here now. We've got the couple moment, and this is completely random direction, and the resultant force. And we also have this direction, the direction of the wrench, the unit vector in that direction. So next, let's get, as a vector, let's get the M parallel and M perpendicular. Let's get those as vectors. So M parallel, the couple moment in the parallel direction, how do we project a vector onto a specific direction? We just dot it with the unit vector in that direction. So M, the resultant, and we'll just call it parallel, and this is as a vector, what we're going to do is say this MR about 0.0 dotted with the unit vector in the parallel direction, but that just gives us the magnitude of the projection, right? We want to then multiply this by the unit vector in that direction to get the vector, right? So dot products are easy. Let's do the dot product. Let's do this, the resultant couple moment dotted with the unit vector in the parallel direction. That's just, okay, 100 times minus 0.738 plus minus 620 times minus 0.527 plus 800 times 0.422. 590.5. Okay. But this 590.5, that's the magnitude of the parallel component. Right? That's how this works. You first get this dot product here gives you the magnitude, the projection of a vector onto a direction, the magnitude of that. And then we just multiply by the unit vector in that direction if we want to get it as a vector. So this 590.5, that's the magnitude of this M parallel. And that's one of the things that the question asks us. What is the magnitude of the force and couple moment of the wrench? Well, for the wrench, the magnitude of the couple moment on the wrench is M parallel, right? That's how you create the wrench, M parallel. So that's going to be one part of our final answer. The M parallel, this isn't a vector, this is just a magnitude, is 590.5 Newton meters. And also this force is another part of the magnitude of the force. The magnitude of the force and the couple moment. So we've got these two parts of the answer. Okay, but let's finish getting this vector here. So 590.5, now we're multiplying it by the unit vector, so times minus 0.738 minus 435.8. Let's do this. Okay. Minus 311.2. Okay. $249.2. It's Newton meters. Okay. Now we have the couple moment in some random direction, and we've got the parallel component. Well, what does that mean? It's broken down into its components like that. Again, this is a random direction. Here's M parallel. This is M parallel. Right? M perpendicular plus M parallel is the couple moment. So if we want to get MR perpendicular, we just say the main couple moment minus the parallel component, right? Because the perpendicular component plus the parallel component is equal to the main vector. So let's do so 100 minus 435.8. Minus, that's plus. So okay, minus 620 minus 311.2. So that's minus 620 plus 311.2. Minus 308.8. Okay, 800 minus 249.2. Minus 308.8. Wait, no. 550.8. Okay, so there's the perpendicular component. Let's get the magnitude of this. We're going to need the magnitude of this. So we've got 828.1. And this is Newton meters. This is Newton meters. All right, so we've got a lot of information. We've got the couple moment, we've got the force vector, we have the perpendicular vector, the parallel couple moment vector, the magnitudes and directions. We've got the direction of the wrench as a unit vector. But the next thing we need to do is we need to move the force vector off of the point, the origin, so that we can get rid of this perpendicular couple moment. Okay, so to do this, what we're going to do is notice that, so the couple moment and the force vector that we found to start this, they lie in a unique plane in 3D space, right? To specify a unique plane oriented in any direction in 3D space, you can have two axes, right, that aren't parallel. So these two lie in a plane. We're going to be moving the force off of the origin perpendicular to that plane. So how can we find that direction? Well, we can cross FR or M parallel or whatever, or the unit vector, with M perpendicular or the main couple moment. Let's just cross FR with the main couple moment and then turn that into a unit vector. Now, do we do FR cross the main couple moment or the main couple moment cross FR? It doesn't matter, because once we get the direction, that perpendicular direction, we'll analyze it after that to see which direction we're moving. We're going to move the force. But let's just do it like it's shown here. Let's cross FR with MRO. And if you push F with the right hand, push FR to MRO, that will be moving FR in this direction, which is the correct direction. But again, it doesn't matter. We'll be analyzing it after the fact. So, but okay, let's cross FR with the main couple moment. Okay, so okay, but now we want to get a unit vector in this direction. So let's get the magnitude of this vector. Now let's say 1 over this times this vector. Okay, so this is, we're going to call this the unit vector in the D direction. That's the D direction. The unit vector in the direction that we're moving the force. Minus 0.193 I hat plus 0.764 J hat plus 0.616 K hat. Okay, now, what distance do we need to move the force vector in this direction to get rid of the perpendicular couple moment? Well, it's just D times the force magnitude. That distance times the force magnitude is going to be equal to this magnitude, right? 379.5 times D is equal to 828.1. So 2.18 meters. Okay, so what is D as a vector? Right? Going from the origin, what is the vector that goes from the origin to the tail of the wrench? That's going to specify the location of the wrench in space. It's just D times the unit vector in the D direction. So we'll call this, well, not just D as a vector. It's just 2.18 times this, minus 0.422 I hat plus 1.66 j hat plus 1.34 k hat meters. So there you go. Now we have the magnitude of the force on the wrench, the magnitude of the couple moment, and the location at which the tails of the wrench vectors is located at. So we've specified the wrench. But we're not done because we have to answer this specific question that we're being asked, which takes a little more work, right? But we've gotten to this point. We know point P, we know the magnitude of this couple moment, and we know the magnitude of this force and the direction. Actually, so it's not just the magnitude and the direction. So we know point P, and we know these two vectors, not just their magnitude but also their direction. But we're not done. We need to specify. So what you can imagine is we've got the wrench is located, let's say, like somewhere here. That's the tail of the wrench. And then the wrench is kind of directed into the page. Okay. And what they want to know is, so this is like kind of out here in the negative X, positive Y area. So there's the wrench, but they want to know the line of action of the wrench. Where does it intersect the XZ plane? At what X coordinate and Z coordinate does it intersect the XZ plane? That's what they're asking. So how can we find this? Well, what we're going to do is we're going to use the equation of a line in 3D space. Okay, so the equation of a line in 3D space, what you do is we have this line vector. Well, okay, hold on. One thing I forgot to specify is, before we do this, what direction is this? Yeah, okay, hold on. I messed this up. We multiply D by this unit vector in the direction of D, but we could have multiplied D by the negative, the positive or negative direction. So how did we choose the right direction or not? Right? We know this is the direction that's perpendicular to the plane containing the couple moment and the force vector. But do we go in the positive or negative direction? Well, it is the case that since we did FR cross the couple moment, we found the right direction. And you can do this exercise on your own to see why it's the case. But okay, so the couple moment is here. Here's the couple moment. The perpendicular component is going to be kind of like right under it. If it was directed out here, the perpendicular component would be right under it here. Based on the right-hand rule, it will always be that, like, okay, here's the direction of rotation of the perpendicular component. So you can see the force vector needs to come this way, right? Because the force vector is directed up. It's causing that same rotation here. So you can replace this rotation by just moving the force vector out here. If the perpendicular component, or let's say the force was directed down and the couple moment was here. If you did FR cross M, we'd be pointing into the page, right? And that's what you want. If you to remove the couple moment, you want to move the force over here, right? That's the same direction of rotation as this couple moment. They're both causing rotation here. Let's say the couple moment was over here. Well, the perpendicular component would be here. That's causing rotation in this direction. F cross R is into the page. That's what you want, right? So if you do F cross the couple moment, that will give you the right direction of rotation, but you don't have to think about it. You don't have to memorize that. You just have to look. You have to do a mental exercise and look and see. So like you could plot the force in the couple moment, right? So you could do like a rough plot of the direction of the force and the direction of the couple moment and see, okay, if I'm crossing, if we did, to get this unit vector, we did F cross R. Is that direction coincide with where I'm going to need to move the force? Like if we plotted this force, it might be something like that. And if we plotted this moment, it would be something, I think, like this. Okay? We did F cross R, or F cross the couple moment, which is in this direction, right? Well, we can look. Okay, so right-hand rule in this couple moment. Right-hand rule. Positive direction is here. Well, okay, where do we need to move the force to replace this the perpendicular would be down here. But same idea. Right-hand rule, here's the rotation. Okay, so where do we need to move the force in this direction? And to the left or to the right? To the right. So that's the positive direction here. So we did it correctly. Okay, so now the equation of this line. For the equation of a line in 3D, you need a point on the line and a direction on the line. We've got both of those. Here's the point on the line. That's the tail of the vector. And here's the direction. You take the point, so the I component, 0.422 plus t times the direction. It's a parametric equation, plus 0.193 t. I hat. For the equation of a line in 3D, it's parametric. Plus 1.66 plus 0.764 t. J hat. Plus 1.34 plus 0.616 t. K hat. Oh, wait. No. Sorry. The direction is not the direction of D. The direction is the direction of the wrench. What is the direction of the wrench? It's this direction. There's the direction of the wrench. So, okay, 0.422, well, it's minus 0.422. So minus 0.422, there's the point, plus t times the I component of the direction. So minus 0.738t. Okay, 1.66 plus, but this is going to be minus 0.527t. And then 1.34 plus 0.422t. Right? We've got a point on the line in the direction of the line. The direction of the line is the direction of the wrench. Okay. But now we're trying to find a point on this line, but we know a property of this point. What do we know about this point? The y component is equal to 0. So let's set this equal to 0 and solve for t. That's 1.66 divided by 5.27. Oh, no, 1.66 divided by, no, wait a minute. 0.527. .15. Okay, so now to get the x coordinate and the z coordinate, just plug in t is equal to 3.15. So, all right, x is equal to minus 0.422 minus 0.738. Okay. Okay, minus 2.75. Okay, z is equal to 1.34 plus 0.422 times 3.15. Positive 2.67. All right, so it intersects the xz plane at x is equal to minus 2.75, y is equal to 0, and z is equal to 2.67. And there you go. Now we've answered the entire question.